We all remember one small step for man. But today, the mission, it's really evolved, hasn't it?
Oh, absolutely.
We're seeing this global push, Chandrayaan, Artemis, and it feels like they're asking a much bigger question now. Can the moon actually become, well, humanity's second home?
That's long-term vision,
Can
definitely.
we genuinely sustain life up there?
That's the goal. But we have to be realistic about the challenges. I mean, it's fundamentally hostile. These missions, they're basically scouting locations in an environment that's, well, it's not designed for us.
Okay, so what are the biggest immediate roadblocks? Let's break them down.
Right. You've got three critical survival challenges right off the bat.
Number one.
First, there's basically no atmosphere, no air to breathe, obviously. That's a big one.
Okay, fundamental. What else?
Second, the temperatures, they are just brutal. You're looking at daytime highs of like plus 120 Celsius,
Wow.
and then nighttime lows plummeting to minus 170 Celsius. Just extreme swings.
Unbelievable. And the third?
And third, something maybe less obvious but just as dangerous is the radiation. Constant high-energy radiation hitting the surface.
Because there's no magnetic field like Earth's.
Exactly. Earth's magnetic field protects us. The moon doesn't have that protection, so you're constantly bombarded.
Okay, atmosphere, temperature, radiation. That sounds daunting. So where's the hope? What changed to make this seem feasible? There must have been a breakthrough.
There absolutely was. The game changer, the thing that shifted everything, was confirming large amounts of water ice.
Water. Frozen water.
Yes, frozen solid tucked away in these permanently shadowed craters, mainly near the moon's south pole. And this isn't just, interesting science. It's the key, the absolute foundation for humans being there long term.
Right. I get the drinking water part. That's obvious. But how does it help with, say, the air problem?
Well, that's the beauty of Atrios. It's incredibly versatile. You use electrolysis, basically running an electric current through it, to split the water molecule.
Into hydrogen and oxygen.
Precisely. And that oxygen, that solves your breathing problem inside a habitat. You create your own atmosphere locally.
Okay, drinking water, breathable air.
Yes.
That's huge. But you mentioned fuel earlier. How does water become rocket fuel?
That's probably the most revolutionary part. The hydrogen and oxygen you get from splitting water. That's literally rocket fuel components.
Okay.
Now think about launching missions from Earth. So much of the cost and weight is just lifting the fuel itself out of Earth's gravity. It's incredibly expensive.
The tyranny of the rocket equation, right?
You got it. But if you can make your fuel on the moon using that water ice...
You don't have to launch it all from Earth anymore.
Exactly. It completely changes the economics. The moon stops being just a destination and becomes, well, a refueling station, like a cosmic petrol pump.
A space petrol pump. I like that.
It really enables everything else. Missions to Mars, deeper into the solar system. They become much more feasible if you can top up the tank on the moon.
Which brings us to the actual plans, like NASA's Artemis program. They're talking about a permanent Artemis base camp by the 2030s. That sounds less like an outpost and more like infrastructure.
It is. This isn't just flags and footprints anymore. It's about sustained presence. But building it requires solving those other problems, the temperature extremes, the radiation.
So how do you build shelters that can handle that? You can't exactly ship tons of concrete.
No, definitely not. The plan relies heavily on using what's already there. Lunar soil, it's called regolith.
Okay. Dirt, basically.
Sort of, yeah. Pulverized rock and dust. The idea is to combine this regolith with advanced 3D printing technology.
So printing buildings using moon dust.
Essentially, yes. Large 3D printers would layer the regolith, maybe using a binder or sintering it with heat, to build structures directly on the moon.
Build it locally.
Build it locally. And the great thing about regolith is that it's dense. If you build thick walls, it provides excellent shielding.
Against the radiation and the temperatures.
Both. Thick regolith walls would naturally insulate against the huge temperature swings and block a lot of that dangerous radiation.
So the life we build there won't be natural, it's engineered survival.
Completely. It's man-made life, inside protected, engineered habitats. We have to create the environment because the natural one is lethal.
It's fascinating. The moon, it's always been this symbol in poetry,
Yeah.
stories. And now it's potentially becoming this critical next step. Maybe even humanity's next capital, in a way.
It's a huge shift in perspective, driven by figuring out how to use local resources to overcome these massive engineering challenges.
Right. And that brings up a final thought for you listening. This whole base camp idea hinges on getting really good at 3D printing with regolith right there on the moon.
It's central to the plan.
So think about this. How might the specific architectural techniques, the materials science, the construction methods they have to invent for the moon, how could those breakthroughs end up changing how we build things right back here on Earth? Something to ponder next time you look up.